Hello guys, today we're going to talk about a microscopic interpretation of gases, which leads us to describe what is called the kinetic model of an ideal gas. So first of all, we have to imagine, right, that we have molecules inside a certain volume V. This volume V, we will think that it's inside a system of reference. For example, here I can add a z-axis, an x-axis, and a y-axis. And here in this volume V, I have a number of molecules. And let's say that we concentrate on this molecule over here that has a certain velocity v, where v it's a vector now that has three components, vx, vy, and vz. Let's say also that the side of this cube, it's L. Okay, so it's L everywhere, such that the volume is just L to the power of 3. And now we have to make some assumption if we want to describe a gas in this way. We can make, for example, the first assumption, which is that the molecules don't occupy volume. So basically the molecules are point-like sources, right? Well, the gas, we have to imagine that it's a number of these molecules, a large number of these molecules, which are in constant random motion. So we have to also assume a constant random motion. And we have to understand that now each molecule that hits one of these surfaces, it's going to produce a change in impulse, which brings me to the fact that there is going to be a force applied on that wall, because we have a change in momentum over time. That's what we called impulse in chapter 2. Also, we're going to assume that the time of collision between molecules, but also among molecules and walls, is much, much less than the time between two collisions. So the collisions are happening, but very far away, not very far away from each other, but with enough time between them, okay? So the time between two collisions. Yes. Also, we have to assume that the collision is basically perfectly elastic. You know what it means, perfect elastic collision? It means that the kinetic energy is conserved, right? That we learn in chapter 2 when we talked about momentum. Why am I listing all this stuff? Well, I'm listing all these assumptions because what I'm going to describe to you, it's a model. And as any other model, it's relying on some hypothesis, on some, let's say, constructions, right, that we have here that I now call assumptions, okay? So now the goal, what is it? Well, the goal in this case here today, it's to relate the pressure, the volume, and the time with the property of the singular molecules composing the gas. So we want to relate that to the microscopic behavior of the molecule composing the gas. Okay, so we want to understand finally how somehow the pressure can be described with the properties of the molecules there. Okay, so the calculation starts a bit like this. Okay. It tells me that first of all I need to consider a wall of this box. So let's imagine that here I have one of these walls, and let's imagine that I have one of this molecule that by chance, okay, is one molecule that is going in the perpendicular direction with respect of the wall, and we have as velocity Vx, Vy, and Vz for this molecule, and we have oriented somehow the axis in the same direction. So we have that the x-axis is directed in this way, and then we have the z-axis, and then we have the y-axis this way. So now, what is the initial momentum of this particle? Well, it's actually mvx in the x-axis, okay? Let's start to analyze what's happening in the x direction. What is the final momentum in the x direction? Well, the molecule is going to bump on the wall and then come back, right? And if it's coming back probably in the same direction, but then it means just that the momentum is going to be minus m times vx, all right? So what's the change of momentum? Well, the change in momentum is the final momentum minus the initial momentum, which gives me minus m times vx minus m times vx. So we're talking about minus 2m times vx. What I want to calculate now is the impulse on the, the force, right, that I have on the wall. So I have that, so this is going just to be the change in momentum divided by a certain amount of time. So it's just going to be minus 2m vx divided by a certain amount of time. And what's the time for going to the wall and back? Well, I can calculate that, right? Let's say that this length is the whole side of the cube, right? And I want actually to go back and forth, right? So the distance that I'm covering is 2L. Then the time that it's going to take for the molecule to go back and forth is going to be 2L divided by Vx. And therefore here I will have that this is equal to minus 2m Vx divided by 2L times Vx. So Vx becomes squared. And actually the 2 can cancel out. And I have therefore a result that it's minus m divided by L Vx squared. Now, this is the force that the molecule is applying on the wall. And now for the third Newton's law, I know that there is a force equal and opposite that the wall feels. So the wall is going to feel a force that it's actually equal and opposite. So we're just changing the sign here. So it's just going to be m times Vx squared divided by L.